Hi, Dr. P here, and in this lecture we're going to take a look at Lewis structures, which are a way of representing the structure of covalent compounds. So Lewis structures are a way of representing covalent compounds using what we call the localized electron bonding model. And the localized electron bonding model simply states that a molecule is composed of atoms that are bonded together by sharing pairs of electrons using the atomic orbitals of the bound atoms. So a molecule is composed of atoms that are bonded together by sharing pairs of electrons using the atomic orbitals of the bound atoms. Okay, and I should also make a note that we're only going to focus on the outermost energy level. So, if we've got n equals 2, we're looking at the 2s and the 2p orbitals. And those are what we call the valence electrons. Okay, outermost energy level. Those are our valence electrons. And so I can calculate my valence electrons by simply counting. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. N equals 1 and N equals 2 for chlorine are considered what we call core electrons. And so we only worry about the valence electrons for our bonding. Okay, now there are some rules. So Lewis structures are going to show how the valence electrons are arranged among atoms in a molecule. Now, it's not... Lewis structures are in some ways like oxidation states, oxidation numbers. They are a man-made construct and a way of keeping track of electrons. They are accurate in many cases and not as accurate in some cases. And we'll take a look at some of those exceptions as we go along. Key requirement here if we want to have a stable compound, the atoms have to achieve noble gas electron configurations. Okay, and that means that by sharing electrons, the atoms get to the noble gas configuration. So this happens via electron sharing. So instead of donating an electron, giving up an electron, or gaining an electron like ionic bonds, we're going to share pairs of electrons, so we'll double count them towards the valence shells, we call them valence shells, of both atoms in the bond. Okay, so let me go ahead and write out some rules here. And the rules are maybe a little, I don't know if I'd say boring, but I got to list the rules and then we'll talk more about them. I will mention that I have posted on Canvas, I do have Dr. Pitcher's Guide to Drawing Lewis Structures, Chem 1A version. And it has a summary of the rules. Okay, but I'll write these. I'll write these out so that we've seen them multiple times. Lewis structure rules. Okay, so first of all, some general things. Only valence electrons included. So, for example, if we had, an atom of hydrogen, we would have 1. If we had an atom of chlorine, we'd have 7. And each dot equals 1 electron. So a pair of dots equals a pair of electrons. Now hydrogen can share 2 electrons. And we call that the duet rule, which is just what hydrogen does. Nothing else does it. So we have H with an electron, and we have another H with another electron. And that's the same as if we wrote H, H. And so that line there is what we call a single bond, and it equals 1 pair of electrons that are shared. Okay? Now, helium does not form bonds. So it already follows the duet rule. And then the second row nonmetals carbon through fluorine follow an octet rule. That is, they're surrounded by enough electrons, shared electrons, to fill the valence orbitals, the 2s, and then all 3 of the 2p orbitals. So we call that the octet rule. So remember that, 8. So for example, I could have F with 7, and then I could have another F here with 1, 2, 3, 4, 5, 6, 7. And I'm indicating all of my electrons that are not involved in bonding with dots. So these dots there are lone pairs, and they're non-bonding, as opposed to a bonded pair, which is in my bond. And then neon does not form bonds. So it would just be neon, and it fills the octet rule all by itself. And then we can go down to the next row, and the silicon through chlorine will actually behave similar to carbon through fluorine, although we'll see there are some exceptions. And argon typically does not form chemical compounds, although under very extreme circumstances, argon compounds have been synthesized. They're pretty crazy. And we'll actually see that xenon compounds are something that has been synthesized, that have been synthesized as well. All right, so let's go over the steps then. The first thing that we'll want to do is add up the valence electrons for all the atoms. And then we'll go ahead and we'll use a pair of electrons to form a bond between each pair of bonded atoms. Now, if you've got 3 or more atoms, usually the least electronegative atom is going to go in the middle. Okay. And then you go ahead and arrange the remaining electrons to satisfy the duet and octet rules. So, for example, if we had H2O, we have, let's see, our valence electrons equals 2 times 1, those are for hydrogen, plus 6, that's for oxygen, so it's a total of 8 valence electrons. In this case, oxygen is actually more electronegative than hydrogen, but we can't put a hydrogen in the middle because hydrogen forms a duet rule, and hydrogen will only ever form one bond. So we'll have HOH like that. And now I've used 1, 2, 3, 4 of my 8 electrons, and I'll put the other 2 in on the oxygen. And now, if I cover up my hydrogens, I have 8 electrons. So 2 from each bond, 2, 4, and then 2 from each lone pair, 6, 8. So my oxygen fulfills the octet rule. And if I cover up that, I see my hydrogen has 2 bonds. I'm sorry, it has 1 bond. It has 2 electrons from that bond. So it fulfills the duet rule, so that's good. And same with my other hydrogen on that side. It has 2 electrons in the form of that bond, so it fulfills the duet rule. So we are good. Okay, now we can rearrange electrons if necessary. Okay, and let's look at an example of that. An example of that would be carbon dioxide. So if I have CO2, okay, my valence electrons, I have one carbon, so that's 4, and then I have 2 times oxygen, so that's 2 times 6 is 12, so it's a total of 16. So I can go ahead and I'll stick my carbon in the middle, bonded to the 2 oxygens, and now I'll start putting electrons around. 2, 4, 6, 8, 10, 12, 14, 16. There we go. But carbon here only has 4 valence electrons. So that's bad. So what I can do is I can take a pair of electrons and move it. I'll do this on both sides. And I'll redraw this molecule, carbon having double bonds to the oxygens, and then I've got my lone pairs there on the oxygen. So now I've got 1, 2, 3, 4, 5, 6, 7, 8 on the oxygen. 1, 2, 3, 4, 5, 6, 7, 8 on that oxygen, and I've got 1, 2, 3, 4, 5, 6, 7, 8 on the carbon. I'm happy. Yay. That's good. And then let's do another example here. Let's do an ion, Cn minus. So my valence electrons. Carbon brings 4 to the party. Nitrogen brings 5 to the party. And then my negative charge is 1 electron. So I have a total of 8. That's not 8. That adds up to 10, Wayne. Come on. 4 and 5 is 9 and 1 is 10. 10 valence electrons. So let's do C and N. And if I start putting them around, you know, my carbon here, 4, 5, so 2, 4, 6, 8, 10, that's not so good. I'm going to have to move some of these over. That still won't give me enough. I have to move more over. So I think it's best to have a triple bond, Cn, like that, with a lone pair there and there. So now I've got 2, 4, 6, 8, 10 electrons. My carbon has 2, 4, 6, 8 electrons in its valence shell, and my nitrogen has 2, 4, 6, 8 valence electrons in its shell. And then we don't really care which electrons came from where at this point. I'd put this in brackets and give it a negative charge. In a later lecture, we'll take a look at actually assigning the negative charge to an individual atom in the molecule. We call that concept formal charge, but we'll deal with that later. All right, now there are some exceptions to the octet rule. Sorry about that. Let me tidy this up a bit. So one of these is BF3, boron trifluoride. So boron has 3 electrons, and 3 fluorines gives me 3 times 7, 21, so that's 24 electrons. So boron, F, F, F. And so I could try moving and pushing electrons around to make some multiple bonds, but those actually give me problems with that formal charge that I mentioned here, or that I mentioned a little bit earlier. So we call this an incomplete octet if we have only 6 electrons around the boron in the boron valence shell. And BF3 actually behaves and reacts as if it is electron deficient at the boron. And boron often violates the octet rule in this manner. Now another example, maybe I'll use purple here, is SF6. And SF6 has sulfur, gives us 6 fluorines gives us 6 times 7, so that's 42, so 48 valence electrons. Now the problem is here that, again, because fluorine just likes to form one bond, the best way to do this is stick the sulfur in the middle. And this accounts for everything. I'll put in all my lone pairs here. So each fluorine has 2, 4, 6, 8 valence electrons. I've got the correct number because I've got 8 electrons times 1, 2, 3, 4 times 6, that's 48. But my sulfur is exceeding the octet rule. And the thing to note here is sulfur, phosphorus, things like sulfur and phosphorus and some other atoms, basically anything in the third period on down can exceed the octet rule. So if we get into things in the third period on down, so phosphorus, sulfur, selenium, bromine, it turns out xenon can, iodine can, these can exceed the octet rule because there are d orbitals that are potentially available for bonding, or at least that's the way it's been traditionally explained. The reality of it is a little more nuanced and definitely beyond the scope of this course. All right, so that's sort of the quick version of Lewis structures, if you call 23 minutes quick. I urge you to read the guide to drawing Lewis structures, okay? And there are some things that I didn't talk about. For example, never ever have 5 bonds on carbon. You never exceed the octet rule for carbon, nitrogen, oxygen, okay? You can follow the rules, but I do things a little differently. I'll look for the central atom, and then I'll think about common bonding patterns. And what are common bonding patterns? Well, common bonding patterns are the number of bonds that elements typically form. So neutral carbon will typically have 4 bonds. We could have 4 single bonds, 2 single and a double, 2 double, 1 single and 1 triple, etc. Neutral nitrogen forms 3 bonds and has 1 lone pair. And so the more structures you draw, the more that you'll come to learn these and recognize these common bonding patterns. So take a look at the handout, and I do have a few molecules here, molecules and ions for you to practice on, so definitely practice on those. And we'll do some of this in the group activity this week. All right. Well, I think I've talked long enough about Lewis structures. We'll look at some of the more advanced concepts in Lewis structures, things called resonance and formal charge, in the next video. But until then, stay safe out there. Bye now.